Further, we studied how to integrate a DC microgrid with the AC grid in that model. To understand the present module, energy management of DC microgrid, fellow students required the knowledge of the previous module. For this reason, we are repeating some critical aspects of the earlier module. Now, the module mainly focuses on energy management between DC and AC bus of the DC microgrid. This slide shows the block diagram of the L filter grid tied DC microgrid. In this slide, it is shown that the hardware test bed is developed by interconnecting various components. The AC side of the inverter is connected to the AC grid through L filter. The point PCC shown in the block diagram forms an AC bus where the AC loads are also connected. A Hall effect voltage and current sensor are used to measure the voltage and PCC and current through the inductor. The measured voltage and currents are biased to shift the signal above 0 level. The offsetted output of current and voltage sensors are given analog to digital converter, so called ADC pins of DSP launchpad TMS 320 F28379D. Inside the DSP controller, the ADC pins read the 3-phase currents and voltages along with the DC link voltages. By using Clark's transformation, the 3-phase voltages and currents are converted to the stationary reference frame from ABC to alpha beta, such as UABC to U alpha beta and IABC to I alpha beta. Further, the control logic generates modulation voltages for generating PWM pulses through EPWM pins of the DSP. These PWM pulses are used to switch the inverter. Now, the grid connected mode of operation. This slide shows the control logic used for interfacing the DC microgrid with the AC grid. The DC bus voltage controller regulates the DC bus voltage at the reference value and generates the AC power reference value. Active current reference is generated from AC power reference as the inner controller requires a current reference. The obtained AC current reference is converted to the stationary reference frame. This current reference is compared with the measured current, which normally gives an error. The error is processed through proportional plus resonant controllers for generating required modulation voltages. The modulation voltages are used for SPWM generation through EPWM pins of the DSP for switching converter switches, commonly IGBTs. The control variables of the PI controller as well as the PR controller can be obtained through proper tuning, ensuring that the stability margin should be more. Now, if you look at the laboratory prototype of the grid tied DC microgrid, this slide shows the block diagram of the hardware test bed. In this hardware test bed, the DC microgrid behavior is emulated through a power amplifier by configuring it with Opel RT. In the Opel RT, the DC microgrid is simulated, which contains PV, battery and variable DC loads. The scaled down DC bus voltages is given to be the analog input of the power amplifier. The current fed to this power amplifier is given to the analog input of the Opal RT. This creates a PHIL loop between the Opal RT and the power amplifier. The combined operation of the Opal RT and the power amplifier emulates the DC microgrid behavior completely. The behavior of the AC grid is mimicked through Synergia programmable grid emulator, semicron 3-phase IGBT based PWM inverter is used as a bidirectional DC-AC converter between the DC bus and the grid. The control logic shown in the previous slide is implemented in the DSP controller. The floating point Texas C2000 DSP controller of the TMS 320F28379 Delfino type is used in this hardware test bed. Now, moving to the hardware demonstration, let us have a look at the hardware test bed, and this test bed is developed by interconnecting various components such as grid emulator, DC microgrid is emulated through Opal RT, IGBT stack, filters, DC loads inside the Opal RT and AC load which is externally a bulb load. In this hardware test bed, the DC microgrid is emulated through the Opal RT which forms a DC bus. The emulation of the DC microgrid will be shown in the later part of this video. This DC bus is connected to the DC input side of the IGBT stack. The AC side of the IGBT stack is connected to the input side of the MCB through an inductor. The output side of the MCB is connected to the grid emulator. The bulb is connected at the MCB point which acts as a parallel AC load. Most of the components used in this hardware test bed have been explained in the previous module. In this hardware test bed demonstration, we are interested in showing how to program the desired control system in the DSP controller through MATLAB embedded coder will be explained in detail. Further, the emulation of the DC microgrid through the power amplifier by using Opal RT will also be explained. Finally, a test case demonstration shows the power exchange between AC bus to DC bus of the grid connected DC microgrid. DC microgrid emulation through power amplifier using Opal RT with the help of power hardware in loop experimentation, so called PHIL experimentation, the DC bus of the DC microgrid is emulated through a 4-quadrant power amplifier. The DC microgrid is implemented in the Opal RT which runs on RTLab software by calling the MATLAB Simulink files. The DC microgrid consists of solar, BESS and variable DC load connected to a DC bus. This DC microgrid is initially simulated in the MATLAB. Now, the simulated DC microgrid is rearranged in the form of a master subsystem and control system. The master subsystem consists of power sources or control/computational algorithms. At the same time, the console subsystem consists of variables that need to vary in real time operation. To emulate the DC bus, voltage through power amplifier, the DC bus voltage is sent out through analog out of Opal RT by scaling down to 0 to 10 level, which is the power amplifier analog input voltage level. The power amplifier is configured to external mode, which gives the voltage corresponding to the analog input voltage value. Now, the analog output of the power amplifier is given back to the analog input to the Opal RT controller. This input signal is the input to a current source connected at the DC of the DC microgrid. Here, the analog output of the power amplifier is the current signal that either feeds or draws from the power amplifier. The same current signal is either fed or drawn through a current source at the DC bus of the DC microgrid inside the RT lab of the Opal RT. This looping system between Opal RT and the power amplifier effectively emulates the DC bus of the DC microgrid. The output of the power amplifier is connected to the IGBT stack at the DC input side. The output side of the IGBT stack is connected to MCB, which forms an AC bus at which the AC load is connected parallel to the grid. Here, the AC load is a bulb load and the IGBT stack acts as an interface between the AC grid and the DC bus, which is called an interfacing converter. The control system of the IGBT stack is implemented in the DSP controller. Implementation of the control system in the DSP controller as follows. The voltage and current measurement are given to the DSP controller by using biasing circuits. The accessing of ADC and PWM pins of the DSP controller is explained in detail in the previous module. In this module, we are very much interested in showing the implementation of the control system within the DSP controller. Initially, the grid tied DC microgrid is simulated in the Simulink and the corresponding control is implemented in the same Simulink. Make sure that this simulation should run perfectly. After simulation, remove the plant and keep the control system that is required in DSP. Configure the DSP launchpad at the hardware setting of the Simulink setting pane. Before configuring the launchpad type, ensure that the required softwares are needed to be installed in the system as per the guidelines given by MathWorks. After the configuration, the ADC pins must be configured to get physical signals into the DSP controller. Make sure that the ADC pin configured inside the Simulink is the same as the pin the signal needs to connect. The control system processes the signals and generate modulation signals, which are used to generate PWM signals. These PWM pins need to be configured to take out from the DSP board. Now, moving to the hardware demonstration test cases, we will consider the first case. As we know, the DC microgrid is emulated through the power amplifier and the control system of the interfacing converter which is between the AC grid and the DC microgrid, is implemented in the DSP controller. In this test bed, the interfacing converter has been given the responsibility of controlling the DC bus voltage, which is at 400 volts. The first test case that we need to observe here is if the sum of the power generated by the PV and BSS is more than the DC bus load, the power flow from the DC bus to the AC grid, and to achieve the above two phenomena and to demonstrate this test case, we assumed that the power generated by PV and BSS are constant and the DC load is varied in steps. By looking at DSO, we can clearly witness that the decrease in DC loads increases the current magnitude. Looking at the power amplifier power sign, which is positive, means the power is flowing from the DC bus to the AC grid. Now, moving to the second test case, similar to the previous test case, the power generated by PV and BSS is less than the DC load connected at the DC bus. By looking at the DSO, we can observe the increase in the DC load reflects the current magnitude. Looking at the power amplifier power sign, which is negative, means the power is flowing from the AC grid to the DC bus. So, earlier it was DC to AC grid and now it is AC grid to DC bus. The DC bus voltage is always regulated to 400 volts. From these test cases, we have witnessed the energy exchange between the AC grid and DC microgrid. Now, moving to the references, all the test material which has been presented before you, we have referred the following references very closely. However, I also suggest you to refer important textbooks and many more references for your kind consideration. To conclude, we have experienced how to use a DSP controller in applications of grid integration of renewable energy sources and DC microgrid, etc. The significant benefit of this lecture is that the students can develop their own control system to control a DC microgrid with low cost controllers like DSP controllers. With this, we are coming to an end of today's lecture. Thank you for your kind attention. Thank you. Very good morning, and today we are going to discuss the topic titled Demonstration of PHIL Experimentation for Symmetric and Asymmetric Fault Analysis of Grid Connected DFIG Wind Turbine. In this module, we will discuss the very detailed explanation of power hardware in loop experimentation. The power hardware in loop, popularly known as PHIL testing, involves connecting real power hardware to the simulated network in a closed loop. Now, the power hardware in loop simulation, power devices such as renewable generations like wind or solar, and their inverters that are part of the system network are interfaced with the simulator that is run on the real-time digital simulator in power hardware in loop experimentation. Power is exchanged between the RTDS and the external device via a power amplifier in the PHIO. Now, looking into the DFIG hardware setup, digital to analog D2A converters are used to convert the RTDS voltage or current signal into analogous signals at electronic level with a voltage range of plus or minus 10 volts and current drive in the microampere range. Such voltage and current levels are much below the test power devices operating voltage and current range. As a result, in PHIL simulation, amplifiers are needed to scale the signals sent from the RTDS to those needed by the test equipment. Also, to bring to your notice that due to the external devices integration into the power system network, the stability and accuracy of the interface are significantly influenced by the timing and quality of the signals sent back and forth between the devices and the simulator. Digital simulators like the RTDS, which employ the electromagnetic transients algorithm, can mimic the network reaction in a time step as quick as 50 microseconds. The interfacing DFIG device, that is the part of the network, requires the exchange of voltage and current between the digital simulator and itself. The current that results due to the application of the voltage to the external device is measured and sent back to the simulator. The sensor is used to sense the signal from the physical hardware device and feed the signal to GTAI through the power amplifier. The test demonstration of GTAI card. Now, we will see a small test system that is used to demonstrate how the signals from voltage or current sensors feed the signal from GTAO, GIGA transceiver analog output card and GTAI, GIGA transceiver analog input card of the RTDS. In the function generator, we generate AC signal of RMS 3 volt and feed to the GTAI analog to digital converter card. The GTAI card is an 12 channel RTDS hardware component which is mounted in the cubicle. This signal is reflected in the RSCAD runtime and is received by the GTAI digital input component in the RSCAD. It is to be marked that the function generator can be thought to be input of voltage or current sensor sensing signal from the power hardware device. The device can be high power rating device like solar or wind generation or battery, or even we can think it as a EV charger. If we give the signal to another controller to generate PWM pulses, it will be a control hardware in loop. Let us see this small demonstration in which a 3 volt RMS sinusoidal signal input is set in the function generator. The signal is then sent to the GTAI card of the RTDS. The GTAI module in the RS card receives the signal and can be seen in the runtime of the RS card. Let us check the signal in the RS CAD runtime platform. If we now change the voltage to 4 volt, we see the change in RS CAD. Now, in case of test demonstration of GTAO card, the next demonstration is to show the working of the GTAO card, which is basically a digital to analog converter. The signal from RTDS is scaled in the software RSCAD GTAO analog output component, which is then sent to GTAO card. The GTAO card is a 12 channel RTDS hardware component which is mounted in the RTDS cubicle. Inputs to the GTAO model are IEEE 754 double precision floating point numbers. This model converts and scales input signals to 16-bit integers and writes them to the GTAO card via the GTIO interface. All the output signals are sent to the DA converters on the GTAO card at the same time in aligned fashion. The GTAO card's output range is plus or minus 10 volts. Inputs to the GTAO component must be scaled to produce a desired voltage on the output channels of the GTAO card. To show the receiving of the signal from the RSCAD platform to the hardware platform, we have shown a small demonstration where signal received from the GTAO card is shown in the oscilloscope. You can see the RSCAD platform where a sinusoidal voltage is generated, and using the slider we can set the magnitude of the waveform. The node voltage is given to the GTAO module in the RSCAD. The oscilloscope reflects the signal behavior that is received on the GTAO card. Here we had set 4 volt magnitude sinusoidal signal that is shown in scaled down form in the oscilloscope as GTAO card's output ranging from plus or minus 10 volts. We can vary the magnitude and similar trend of variation can be seen in the oscilloscope too. In the PHIL experimentation, the CRO is replaced by the power amplifier which in turn amplify the signal to make it appropriate for the working of the physical hardware. Now, moving forward, let me demonstrate you the PHIL experimentation using the wind emulator present in our laboratory. As you could see the DFIG hardware setup, a DFIG WTG of rating 2.2 kilowatt hardware setup is connected to the distribution network simulated in the RTDS via a power amplifier. In the network we can see in unit 3 a utility grid of 11 kilovolt that is supplying through the transformer and providing 0.4 kilovolt to the bus number 3. The bus number 3 is then connected to power amplifier using a GTAO card. In the power amplifier, the mode is set to external to receive signals from the GTAO card. We can see the voltage reflected in the panel. The voltage is fed to the main supply of the setup. The voltage generated at bus 3 of the network simulated in RTDS is scaled using the voltage gain and is applied to the DFIG wind system via the amplifier. The main and the rotor branch circuit breaker is switched on and the DC link is charged initially to 317 volt. The power amplifier voltage information is passed to the PLL of FPGA controller to extract grid phase angle. Then we enable phase locked loop and check the reference theta with the phase A voltage. Once the DC link is charged, we enable the GSC control to maintain the desired DC link voltage, which is set say 30 volt greater than DC link voltage, that is 350 volts. The rotor of the DFIG is rotated at 900 RPM, which is 10% of the slip, with the help of the DC motor. Further, the DC motor is governed through armature voltage control method by using the chopper, thereby emulating wind characteristic. In this case, the wind velocity is close to 7 meter per second. Initially, the RSC is called to obtain recovery voltage and phase angle such that the DFIG wind system synchronizes with the grid by closing the relay contact. The run time of the RSCADE platform is shown. First, the system is run on the open loop, that is wind emulator output is not fed back to the system as the grid is not synchronized with the stator of the DFIG. After the grid synchronization, RSC is optimized to extract maximum power at the operating wind speed. Now we can close the loop to form the power hardware in loop. Moreover, during normal condition, The 2.2 kilowatt of DFIG is used to feed 25 kilowatt of active power to the distribution grid simulated in RTDS via power amplifier. This is possible with the gradual increase of current fed to the RTDS. The behavior of the DFIG system is analyzed during symmetrical fault case 1 and asymmetrical fault case 2 in the distribution network. In order to test the behavior of the DFIG wind system at the most severe unbalanced voltage, the phase to phase asymmetrical fault is considered in the analysis as the phase to phase fault results in a larger negative sequence component in the voltage than the single phase fault for the same depth. Further, a comparative study has been carried out to realize the severity of the asymmetrical fault with respect to the symmetrical fault. The DFIG wind system is exposed to the symmetrical fault with dip in the stator voltage of 50% of its nominal value in each phase for 5 cycles, that is 0.1 second duration. The PHIL experimentation results is presented in the figures. The voltage dip at first affect the stator flux as it is connected to the grid directly. The sudden transition in the stator flux induces high rotor voltage whose effect is reflected in the RSC and GSC current as disturbance. This disturbance in the converter current leads to overshoot in DC link voltage. Phase current and corresponding voltage variation is obtained from RTDS, result that highlight the symmetrical variation in all the 3 phases. The active and reactive power variation during the fault can be observed in figure shown below. The DC link voltage for both symmetrical and asymmetrical faults appears to be constant in figure because the voltage scale per division chosen is 100 volts. The voltage deviation of 5 to 10 volt is not observable in the figure. Under similar system working conditions, asymmetrical fault is introduced and the results obtained are shown in the figures. The system is subjected to the fault type of line to line in the B C phase. The dip in the stator voltage in the phase B and C is 50% of the nominal value for 5 cycles, that is 0.1 second duration. There is even greater disturbances in the RSC and GSC current when subjected to asymmetrical fault as seen in figure. The reason for the DC link voltage suit due to the limitation of the converter to cope up with the high inrush current flown through the rotor. Further, line to line fault allows asymmetrical variation in voltages, and the presence of higher negative sequence component leads to larger variation in active and reactive power as presented in the figure. A clear distinction between the symmetrical and asymmetrical fault is as shown in the figures, which highlights the considerable difference in flux, speed of the rotor and in the DC link voltage variations. In asymmetrical fault, the reason for increased variation in flux during the transient period is due to the presence of negative sequence component of voltage in the stator, which induces relatively higher rotor voltage. The settling time for the speed seems to be very large in the case of asymmetrical fault due to the effect of negative sequence component. This leads to the larger variation in the flux, which further increase perturbation in the RSC current, and the extra power accumulated in the rotor causes more perturbation in the speed. In asymmetrical fault, the reason for increased variation in flux during the transient period is due to the presence of negative sequence components of voltage in the stator, which induces relatively higher rotor voltage. In this work, the analytical view of PHIL experimentation of DFIG WTG under the symmetrical and asymmetrical fault is shown in detail. It can be deduced from the results that the asymmetrical fault greatly influence the transient response of the system. The asymmetrical fault effect can be summarized in the following terms. There is a almost twice variation in flux while the speed varies drastically. Second, there is a increased disturbance in the RSC and GSC current. There is a rise that is shoot up in the voltage of DC link due to the accumulation of energy at the DC link capacitor. The huge fluctuations in active and reactive power injected to the grid also indicates the severeness of the asymmetrical fault. To conclude, in this lecture we have learned PHIL experimentation for symmetric and asymmetric fault analysis of grid connected DFIG wind turbine in detail. I am confident that this content may encourage you to carry out certain laboratory experiment and further research in the same field. Thank you.
Well, so with this, we conclude our day 19, second last day of our FDP. So tomorrow is the day 20, which is the last day for FDP. So tomorrow we will try to get sir connected with us online, and then he will conclude the FDP. Otherwise, if he is not available, then maybe some other time, whatever demonstration part we have covered, that will be concluded by him. So, with this note, we end for today, and we will meet tomorrow at same time, 5 p.m. Thank you.